All right, the next section is wave equation, and now this section your textbook at least give the solution in a kind of reduced form, in the reduced and in the sense that it's discuss just the 1D problem. The 1D wave equation is like the textbook equation 9.89, so that equals to positive square sine positive x. It's one spatial variable x, and then the c would be the speed of the wave, right? So that's 1D wave equation. And in 3D, what is that? If this 3D, you know, the 3D wave equation, right? What should be the right hand side? L square, right? Laplacian, yeah. Laplacian side. So that's just it's the same basically. It's just if it's Laplacian, but its psi only depends on x, then you reduce this. Right? All right. For the 1D problem, the solution, and we actually did that, I think, in the past in a few sections before. The solution is general solution is any general function f x minus ct and plus another general solution x plus ct. That's two general solution because there's second order in time, so you have two general solutions, but the argument is different. This is x minus ct, this is x plus ct. Right? Is that okay? So you can check either one of them that as a solution by just substitute it back to here, right? And so that is straightforward because when you substitute this like the f here, substitute in this term, so you basically take the second derivative of f with respect to its argument, whatever this argument you call it. So it becomes f double pi. But then you each time you take a derivative, you pull out the minus c because you need to take a derivative of the argument with respect to t. That will pull out minus c. And second derivative will pull out c squared, so cancel the c squared. So the left hand side just f double pi. And the right hand side is trivial because this is just proportional to x. So that is also psi double pi. Right? So that you check is a solution, and likewise g is the same because that will put our c squared is a minus c squared, which is still give you c squared. So these are the two solutions, right? So quite straightforward, right? So obviously the property of that is just whatever this functional form, this one will propagate to the right. So the initial f, the fx, the initial fx is like that, right? That's t equals 0, and at the later t larger, positive time, positive t, then you go to here. So this distance will be ct. We'll be just moving the same function, center now at the position ct instead of the origin. Right? So that kind of the property of that, and likewise, if g is whatever g is, if g is like that, if this is gx, it will propagate the other direction. So at the time t, then we'll move to the left ct, so we have g function will move to the left. So just initially, if you have f and g plus, and add the two together would be the initial psi, right? Because psi x0 is just fx plus gx, right? So initially we'll be just adding the two, but then after a certain time, then we separate. One is going to the left, one is going to the right, left, and then the other going to the right. Okay, so that's the property of this solution. Okay, yeah. So kind of straightforward. And then the text will also present a general form of the solution given the boundary condition that psi at 0, and then partial psi, partial t at 0. So you can say partial psi, partial t at x0. Or you might as well write it psi t x0. And that is given by whatever that. So this is a given function, assuming this is a function form. In order to get the general solution, in order to get the solution for psi, given the initial condition, this one and that one, you need two conditions because it's again second order in time. You need its value and its time derivative. Okay, and that you need to solve f and g by given this initial condition. And in that case, we take the derivative and set to 0. That the first term, the f term put or minus c again, and then you have the f prime. That the basic f prime is just the f dx, right? And then the second term put all c and g prime. Okay, and now you want to solve the f and g given by these two conditions, right? And the idea is what you can do is this is like a differential equation. There's different way to solve it. I suppose you can solve it by taking a derivative first, right? The textbook doesn't seem to be doing that. Or maybe the textbook or textbook do is because both are derivative of x, and just integrate that first. This is like a differential equation, but for both solutions, just f minus g. This is minus f plus g. But anyway, if you integrate it once, you get x partial psi partial t. You like me, or we change that to x prime, right? And then that is, I mean, depends on the boundary condition. That given by the textbooks do a trick. Instead of a given by, usually this is an x, right? But now given by what you can do is integrate that. Integrate this one is partial psi partial t x0 dx. That is given by x minus ct to x plus ct. I mean, it's divided by 2c for later convenience, I suppose. Right? And then 1 over c2, and substitute this into here. X minus ct, x plus ct. And you have cancel the c, you have g, so basically whatever that function is, d, g, dgx, or you can say x prime, and then minus df, x prime, dx prime. I mean, at first we can change that to x prime first, because we have another x, so to avoid confusion. You just change the variable to different variable, right? And then that you just use the how you do integration of a total derivative. So that will give you the x plus ct minus gx minus ct, right? And then minus f x plus ct and plus f x minus ct. Okay. All right. So that gives you one equation, and now you need two other equation because what we wanted to solve is this one. We want this one and this one and this one. We want this one and this one, right? But we have extra term which we try to find another equation to cancel it, and I think you're using this one, but then you just substitute it in a different functional form. So substitute this in first evaluate at x plus ct, and then plus another term, so x minus ct. That will give you the substitute f and g in here. So f x plus ct plus g x plus ct, and then plus f x minus ct g x minus ct. Now remember that we want this two. We want this one and that one, but we don't want this two, right? So we can see if we can cancel this two. This one is this one, and this one is this one, and both have the same sign, right? This is negative sign, this is positive sign, and these are the two that we want, which has positive sign, and these are the two that we want is positive sign. So we add the two equations, then we have 2 times of what we want, but cancel with this one half factor and subtract all the 2 terms that we don't want, this 2 terms that we don't want, right? So basically add this 2 and you'll get this one, right? This is this plus that, or this plus that, right? You just add the 2, so the solution will be just 1/2 of f psi x plus ct 0. This is the initial condition, plus psi x minus ct 0. And then plus 1 over c integrate x minus ct to x plus ct psi positive t 0 x positive. Okay. Finally again. It's okay. So that's I mean, once you know that this is a general form, the rest is just to figure out how you get this 2 function from the given initial condition. So it's just need to struggle with it a little bit and finally get this form. Is it okay? Yeah.
How do we get the dg by dx? Right? Didn't we differentiate f with respect to t?
No, this is a function. This is a derivative over the argument, right? The positive psi, positive t. This is take the partial derivative of that, and then set t equals 0. You just write one more step, positive psi xt. Before you set it to 0, that is given by this one minus c f pi x minus ct plus c g pi x plus ct. The pi means taking a derivative with respect to the argument of the function. The argument function is x minus ct, or this one. Argument is x plus ct, so that's pi is with respect to the variable. Okay, so right, then this is just the set t equals 0. So once you have that, you set t equals 0 here, and get rid of this t, get rid of this, so both becomes function of x. Okay. And obviously, again, you can substitute this back to your equation. This is what became that is the solution of this one. And again, you can do the substitution back to the equation and check for yourself. This is indeed a solution and satisfy the initial condition. Like you set t equals 0. You set t equals 0, obviously the integral is 0. This is 0. This is 0. Both are the same. You cancel with 2. You get exactly the same initial condition. Okay, and likewise you can check the derivative. So that's the solution of the 1D equation. Is that okay? How much time do I have? Take a little bit of time. Any more questions about this? So the 1D is kind of trivial. It's straightforward to write down the equation. What about 3D? What about this Laplacian? So how do you try to solve? Like given us the same kind of initial condition, let's erase all this. Now for 3D, say like psi is now as function x and t, right? And the initial condition will be like psi x 0, like a given initial condition psi 0, right? And then likewise, you can say positive psi positive t of x 0 is some psi or whatever psi pi 0, probably, or psi tilde, whatever, or another, not psi, or maybe 8 0. Right, another function. Given this 2, and then solve for the 3D wave equation, how do you solve it? What method do you use? Any suggestion? One D is trivial, right? 1D, we just showed that it's trivial. How about 3D? Need something separable? That probably can do. Yes, separable. Any other suggestion? Separable is it's probably can do. Probably can do that. And Fourier transform, yeah, because we learned that. That's the purpose of my question, because we changed the order. The textbook has a quite strange order, put the basic thing way to the back. The Fourier series, Fourier transform, which are the basic how to solve problems. So if you know Fourier transform, that make it easy, right? Because just write down the Fourier transform of psi. So psi x. Now we have Fourier transform in x rather than t, because we want to keep t. This is an initial value problem. Given the initial value and the time derivative, we might as well solve the initial value problem. So keeping t, but then transform x. So x will be. You need a 3D transform, but you know how to do that. We have this. Given another symbol for the Fourier transform, that you can use the wave vector as your transform variable. e to the I k dot. Okay, right? That's how we learn the Fourier transform, right? So that's the Fourier transform, and then we know that how you transform a Laplacian, right? In Fourier transform, so basically write down the transform equation for this equation. After you transform it, the time part is this changing this this side to this side too. Right? Okay. Also t squared. And the right hand side, you remember that just put or minus k squared. Right? And now you know how to solve this, right? What is that? This is it's a simple harmonic oscillator. we did that many times in the separation of variable, and many cases we get the simple harmonic oscillator equation, right? So now the solution side will be so you have general coefficient like a or whatever, a as a function of k, because we are solving t, so the coefficient can still be a function of k, and the e to the I. In that case, k, because you multiply c in here, the ct, ckt, and then plus b. E to the minus the two independent solutions, these two solutions. I mean, you can use sine and cosine, but for Fourier transform, is using the exponential is sometimes easier than the sine and cosine, right? So that's the general solution, but that's in Fourier transform. So what you need to do is to substitute this back to here, right? And just write down sine xt is 1/2 pi. So you have, and then you have two terms. One is a k e to the I k dot x plus c kt. The other is e to the I k dot x. K dot x is from here and minus c kt. That's the general form of the solution. Now it's not done. I probably won't solve the whole thing now is to set a two coefficients a and b by from the given boundary condition, given initial condition is size of 0 and a is of 0, right? It's basically matching the boundary condition. Hopefully. So one way to do it is just now set t to 0. So that t to 0, when you set t to 0 is size 0 x is given by this. You have this a, and then set t to 0, and you can combine the two because both now are e to the ik dot x, right? Plus ek e to the ik dot x. Wait, I forgot the integration variable. This is dqk. Right. Now another condition, because we need this one a to 0. We need to take the positivity of that, which will, but this one, the positive of that positivity will put our minus I times c times k in front of here, and then minus ick in front of this one. right? But and then you set t equal to 0, so that would give you a to 0. For instance, you see that a to 0 x over here, 1/2 pi. And remember what we pull out is I, C, K. One is positive, the other negative. Well, I have too many brackets. I don't need that many. Okay. And then I C K and then A K. The other is negative. A K. E to the I. Dot X. Right. So now you have two equations from the two condition, initial condition of the function and the initial time derivative of the function, right? And the goal is to solve the function A and function B as a function of K. Now up to this, can you do that? How? add them, but after you add them, it's still in the function, right? Yeah, multiply ICK, you can add that, but they are in the integral. This is in the integral of K, right? How do you do that? You need one more step, which I probably won't show you, but just talk about that because I'm probably out of time. Yeah, I see. Sometimes, yeah, okay, good. Because this is an integral, right? This is a function. You need, in order to solve the function in the integral, what do you do first? Because this is given, right? Psi 0 and eta 0 are given.
So take the differential.
Take the differential. No, not the differential. This is a given function, psi sub 0. This is also a given for eta sub 0. And they are function of x. Then what can you do? Can you do a Fourier transform of this one? Or, yeah, you can find a Fourier transform of psi sub 0 and eta sub 0, right? Let's write it here. This is equals to this is psi 0 tilde. That depends on k, right? That's just and then e to the ik x. Okay, and this is eta sub 0. Okay, e to the I dot x. Okay. Right. Yeah. Now both are in the integram. Now you can set the integram to the equate the integram. So this integram equals to this one including this ICK term equals to this one. Now you can solve by what you said, subtracting or add them and get A and A. And A as a function of K, B as B function of K in terms of size 0 to K or eta sub 0 K. Okay, so that's the step. But then how do you get this? How do you get size 0 to eta sub 0 T? You still remember the formula? Yeah, inverse transform. Well, this is actually inverse. This is calculated transform. This is just calculated transform given the function. But, okay. Well, I still have some time to write it down for you. Right? You just you see that I'm using the symmetric notation, which make the transformer inverse transformer easier. The size of 0 to k will be just the same factor, and the size of 0x, and except you change this to minus sign equal x, right? Eta sub 0 k. Yeah, this is partial psi, partial t 0. Into the minus ik dot x. Lots of writing. Right. Given these two, you can use the formula to calculate the Fourier transform of the initial condition and the initial time derivative. And then using that, plugged into these two, you can find the A and B function. Once you have the A and B function, put it in here and here, and you get that is your solution. Lots of steps. Right? So from 1D, I erased the formula, but 1D formula is quite trivial. 3D is you can still do that in a few steps. Once you do the the Laplace transform, just do a few steps, and at least formally you know how to solve it. You just go through the step and then write down can write down the form of the solution and know how you solve it by each step. So although the step may be big steps, so these are involving integration, 3D integration in space, and then you do another integration back here, so a double integration. But still, that's a formal solution. Okay, so not too difficult.